Have you ever heard that saying, there's an exception to every rule? Well, today we're diving into a research paper, and it's titled The Entropy Speed Limit as a Universal Rule.
Yeah.
And it explores a possible exception to, well, how quickly disorder can increase, entropy.
Right.
And what's wild is that there may be a fundamental cap on how fast things can basically, descend into chaos.
Yeah.
And this might impact everything from heat diffusion to, get this, artificial intelligence.
You're right. That is a pretty captivating concept.
Yeah.
We usually think of entropy as this ever-increasing, unstoppable force.
Yeah,
It's almost comforting to think there might be, a limit, a sort of universal speed bump for chaos.
totally. For this deep dive, we'll be looking at some seriously cool simulations in different spaces. Euclidean,
Okay.
fractal, hyperbolic, even high-dimensional lattices.
Wow.
And then we'll connect this to, real-world stuff,
Yeah.
like heat diffusion and maybe even quantum mechanics.
Right.
Ready to unpack this?
Absolutely. Let's do it. Okay, great.
To start, let's clarify what entropy really is.
All right.
It's not just a messy room, although that's a good visual.
Yeah.
Entropy is about how spread out energy is within a system.
Right.
Think about heat spreading through like a metal rod.
Okay.
The more evenly distributed the heat becomes, the higher the entropy.
Right. And this idea of energy spreading out applies to information theory, too.
That's right. Yeah.
A random string of letters has higher entropy than a meaningful sentence.
Yeah. Yeah.
It's all about how much information is packed in. So how did these researchers actually go about figuring out if there's a speed limit to this whole entropy thing?
Well, they use computer models to simulate the spread of entropy in different types of spaces.
Okay.
You mentioned Euclidean space earlier.
Yeah.
Which is, basically our familiar 3D world, like a perfectly flat grid.
Gotcha.
Then they got more complex with fractal spaces. Imagine like a coastline that just keeps getting more jagged.
Yeah.
The closer you zoom in, infinitely complex. Okay, starting to get the picture. I remember those fractal videos from the early internet days.
Yeah.
And what about hyperbolic space?
Right. I'm picturing something from a Salvador Dali painting.
That's a good visual. Think of a saddle shape, curving outwards in every direction.
Oh.
It's a space where parallel lines diverge.
Hmm.
And then we go even further into high-dimensional lattices,
Yeah.
which are really hard to picture but important mathematically.
Right.
They have more dimensions than our usual 3.
So they simulated entropy spreading in all these crazy spaces.
Right.
What did they find? Was there any, rhyme or reason to how quickly things got chaotic?
That's where it gets really fascinating.
Okay.
Across all these different spaces, the entropy increase didn't just happen randomly.
Right.
It actually followed a specific pattern. And they were able to capture that pattern in a surprisingly elegant mathematical formula.
Wait, there's a formula for chaos. Okay, I'm officially intrigued.
Yeah.
Break this formula down for us, please. It looks like this. S of t equals a times t to the b over 1 plus c times t.
Okay.
So S to t represents the entropy at a given time. Ta reflects how fast entropy starts increasing initially.
Gotcha.
B determines the early spread pattern. Think of it like whether the chaos spreads slowly like, a accreting vine or explodes outwards like fireworks.
Okay, I'm following so far. So A is the initial chaos burst, and B is like the chaos-style slow burn or Big Bang. What about C?
C is fascinating. It acts as a brake, limiting how much total entropy can build up in the system.
Okay.
It's like there's a cosmic speed limit on how disordered things can ultimately get.
So even in the wildest, craziest spaces, there's this underlying order to how fast chaos can unfold. It's surprisingly comforting, actually. But I have to ask, is this just a mathematical quirk, or does this formula connect to, the real world, like stuff we can actually observe?
That's the really cool part.
Yeah.
It turns out this formula seems to tie in with some of the most fundamental laws of physics. For example, the Bekenstein bound,
Yeah.
which states that there's a maximum amount of entropy a given region of space can hold.
Wait, so the universe has a limit on how much disorder it can handle? Okay, now my mind is officially blown.
What's interesting is that this new formula seems to respect the Bekenstein bound. The formula never produces an entropy value that exceeds that limit. It suggests a deeper connection between the two, and potentially a deeper understanding of how information and entropy are intertwined.
So this isn't just a mathematical game. This formula might actually reflect how the universe works on the fundamental level. Okay, color me impressed.
Yeah.
But we've only just scratched the surface, right?
Okay.
There are connections to quantum mechanics, too.
There are some intriguing parallels.
Okay.
For instance, the Margulis-Levitin theorem, which puts a limit on how fast a system can change states in the quantum realm.
Okay.
The structure of this theorem is strikingly similar to our entropy formula.
So are you saying there's a link between how fast entropy can increase and how fast things can change in the quantum world? That's a pretty big leap.
It is, and it requires more research to confirm.
Right.
But the similarities are there, and they point to a possible um, deep connection between entropy, information, and the quantum world.
Hmm.
And then there's the Mandelstam bound, another quantum limit, this time on how fast quantum states can evolve. Again, we see structural similarities to the entropy formula.
Okay, this is getting pretty deep. But we've been in the theoretical world for a while. Did the researchers test this out with like actual physical systems, like with stuff in a lab?
They did. They looked at how heat spreads in different materials like copper and aluminum, which is essentially entropy increasing in action.
Right.
They used simulations based on materials' properties and compared the results to the formula's predictions.
So hold on, even in the messy real world, where there are all sorts of other factors at play, heat spreading still seemed to follow this speed limit.
It did, which is remarkable. It suggests that this isn't just a theoretical concept, but something deeply embedded in the laws of physics.
Right.
Even in complex real-world scenarios, this entropy speed limit appears to hold true.
All right, so we've got this formula, and it's not just a mathematical fantasy. It actually seems to connect to real-world physics and maybe even the quantum realm. Where do we go from here? What are the implications of all this?
That's what we'll explore next. The potential implications for fields like artificial intelligence and quantum computing are particularly fascinating
Okay.
and perhaps a bit mind-boggling.
Hold on to your hats, folks, because we're about to go even deeper down the rabbit hole.
So we've established this intriguing concept of an entropy speed limit, right?
Right.
And its connection to, real-world physics.
Yeah.
But where does this, lead us? What are the practical implications? Well, one area where this could have a significant impact is artificial intelligence.
AI, really. I'm trying to wrap my head around how a limit on disorder relates to something as complex as AI.
It's all about information processing. Think about how AI learns. It's constantly adjusting its parameters based on the data it receives,
Okay.
trying to optimize its performance.
Right.
This process of, adjustment and optimization, it has a lot in common with entropy.
Okay, I'm listening. Walk me through this connection. How does adjusting parameters relate to entropy?
Imagine an AI learning to play a game,
Right.
right?
Okay.
Initially, its moves might be pretty random,
Yeah.
corresponding to a high entropy state. As it learns, it refines its strategy,
Right.
becoming more organized and efficient, lowering the entropy of its gameplay.
So you're saying the AI is essentially moving from a state of high disorder to a state of lower disorder as it learns, and this entropy speed limit might affect how fast that learning can occur?
Exactly. It's like there's a fundamental limit to how quickly the AI can make those adjustments,
Yeah.
how fast it can reduce the entropy of its decision-making process.
That's fascinating. But isn't the speed of AI learning mostly limited by computing power?
Well,
Wouldn't a more powerful computer just overcome this entropy speed limit?
that's a great question, and it highlights a crucial point. The entropy speed limit might not be about raw computational power,
Yeah.
but about the efficiency of information processing itself.
Hmm.
Even with unlimited computing power, there might be an inherent limit to how fast an AI can, sift through data, extract meaningful patterns, and adjust its parameters accordingly.
So even with the most powerful supercomputer imaginable, there might be this fundamental speed bump, this entropy limit that we can't just brute force our way past.
Precisely. It suggests that we need to be smarter, not just faster, in how we design and train AI.
Yeah.
We might need to develop entirely new algorithms that are optimized to operate within these entropy constraints.
Could you give us an example? What kind of algorithms are we talking about here?
One example is gradient descent, a common algorithm used to train AI. It involves finding the optimal set of parameters for a model by iteratively adjusting them based on the calculated error.
I've heard of gradient descent, but to be honest, it always sounded a bit like magic to me. Can you break it down in simpler terms?
Sure. Imagine you're trying to find the lowest point in a valley, right?
Okay.
You might start at a random location and then take small steps downhill, always moving in the direction of steepest descent. That's essentially what gradient descent does. It calculates the slope of the error function and adjust the parameters in the direction that reduces the error the most.
Okay, I'm starting to get the picture. So how does entropy fit into this this valley analogy?
Think of the roughness of the valley as representing entropy. A very rough valley with lots of peaks and valleys would represent high entropy,
Okay.
making it harder to find the lowest point quickly.
Right.
A smoother valley with fewer obstacles would correspond to, lower entropy, allowing for faster descent.
So are you saying that the entropy speed limit might affect how quickly the gradient descent algorithm can find that optimal set of parameters?
Exactly. If there's a fundamental limit to how fast information can be processed and entropy can be, reduced, it could directly impact the efficiency of algorithms like gradient descent.
That's fascinating. So this isn't just about some abstract theoretical limit. It could have like real-world consequences for how we design and develop AI.
Yeah.
But what about quantum computing?
Right.
We briefly touched on this earlier.
Yeah.
How might this entropy speed limit play out in the quantum realm?
That's where things get really, really interesting. Remember, quantum computing relies on manipulating and transferring quantum information,
Right.
which seems to be subject to this entropy constraint.
Okay.
So there's a possibility that this speed limit could impose fundamental limitations on how fast quantum computers can operate or solve certain problems.
Wow, that's a game changer. Quantum computing is often touted as this, revolutionary technology that will solve all sorts of problems we can't even tackle with, classical computers.
Right.
But if there's an inherent speed limit imposed by entropy, that changes the whole picture.
Absolutely. It might mean that even quantum computers have limitations, that there are certain problems they can't solve efficiently or perhaps not at all,
All right.
due to this entropy constraint.
Yeah.
It also raises questions about how we design quantum algorithms.
Right?
Perhaps we need to develop entirely new approaches that are specifically optimized to work within these entropy limits.
So we might need to build quantum computers that are not only like incredibly powerful, but also incredibly efficient in terms of how they manage and process quantum information. We're talking about a whole new level of engineering challenges.
Indeed, but challenges often lead to, the most groundbreaking innovations. Imagine if we could design quantum computers that operate at the very edge of this entropy speed limit. We might unlock capabilities that we can't even fathom right now.
Okay, now my mind is officially blown again. This is all so incredibly exciting and thought-provoking.
Yeah?
But before we get too carried away with, the possibilities of AI and quantum computing, I want to bring it back to something a bit more personal.
Okay.
What does this entropy speed limit mean for us, for our own brains?
Right.
Could there be a limit to how fast we can learn or think?
That's a fascinating question, and one that takes us into somewhat speculative territory,
Yeah.
but it's certainly worth exploring. After all, our brains are incredibly complex systems that rely on the flow of energy and information,
Right.
just like any other physical system.
So are you saying that our brains might be subject to the same entropy constraints as, a computer or a quantum computer?
Right.
Could there be a fundamental limit to how quickly we can, process information?
It's certainly a possibility, although it would be incredibly difficult to, prove or disprove.
Yeah.
But if it's true, it could have profound implications for how we understand learning, cognition, and even consciousness itself.
Wow, that's a pretty big if. But I'm definitely intrigued. Let's dive into this rabbit hole and see where it leads us. Okay, so we've gone from the universe having a speed limit for chaos to the idea that our brains might have a similar speed limit for, processing information.
Right.
It's a pretty wild thought.
It is. It makes you wonder if maybe those moments of feeling overwhelmed, like when you're trying to learn something completely new, are actually like our brains bumping up against this entropy speed limit.
That's a really interesting way to look at it. So instead of getting frustrated when we feel like, we're not grasping something quickly enough, maybe we should view it as our brains working at their optimal capacity, carefully processing and organizing all that new information.
Exactly. It's like our brains are saying, hold on, I need to integrate this new knowledge into my existing framework. And that takes time and energy. Rushing the process might actually lead to less effective learning in the long run.
So maybe the key to learning effectively is to work with our brains, not against them,
Wow.
respecting those inherent limits. That makes me think about how we approach education.
Yeah.
If our brains have a speed limit for processing information, shouldn't we design learning environments that take that into account? Right.
absolutely.
Yeah.
Instead of, cramming massive amounts of information into short periods, maybe we should focus on creating learning experiences that are more spaced out, giving our brains time to absorb and integrate new knowledge.
That makes a lot of sense. It's like the difference between like trying to drink from a fire hose
Right.
versus sipping from a glass of water. You're
Yeah.
going to get a lot more out of it if you take your time and let it sink in.
Precisely. And this could have implications for, how we design technology as well. Imagine if we could create interfaces that adapt to our cognitive speed limits,
Hmm.
presenting information in a way that optimizes our understanding and retention.
That would be amazing. Instead of like bombarding us with notifications and information overload, technology could work with our brains,
Hmm.
helping us
Yeah.
process information more efficiently and effectively. We could actually learn and grow alongside our technology instead of feeling overwhelmed by it.
It's a really exciting possibility, and it all stems from this fundamental idea that even disorder has its limits, that there's an inherent order to how quickly chaos can unfold, whether it's in the universe at large, in a computer, or even in our own minds.
It's like discovering a hidden set of rules governing the universe, rules that apply to everything from like the formation of galaxies to the firing of neurons in our brains. It's humbling and awe-inspiring at the same time.
Absolutely.
Yeah.
And it reminds us that even in the face of seemingly limitless possibilities, there are fundamental constraints that shape our reality. But those constraints shouldn't be seen as, limitations. They are opportunities to be more creative, more resourceful, more innovative in how we approach problem solving and knowledge creation.
I love that. It's like the universe is saying, here are the rules of the game. Now go out there and play. And within those rules, there's like an incredible amount of freedom to explore, discover, and create.
Exactly. This research has opened up a whole new way of thinking about the universe and our place within it. It challenges us to ask deeper questions about the nature of information, complexity, and even consciousness itself. And who knows what other amazing discoveries await us as we continue to explore these fundamental limits.
Well, I think it's safe to say that this deep dive has left us with plenty to ponder. This idea that even chaos has its limits, and that those limits might shape everything from the evolution of the universe to the way we think and learn is truly mind-blowing.
It is, and it underscores the importance of continued scientific inquiry, of pushing the boundaries of knowledge and challenging our assumptions about how the world works.
To our listeners, thank you for joining us on this incredible journey. We hope it sparked your curiosity and inspired you to keep exploring the amazing mysteries of the universe. Until next time, keep those brains buzzing.